analytical orientation criteria for fractures initiated during drilling and completions. When we drill a wellbore, we are introducing a pressurized cylindrical cavity which disturbs the stress field surrounding the wellbore in a way that the pre-existing stresses, what we call the in situ principal stresses, those are the vertical SV and the horizontal SH max and SH mean, SH max always bigger or equal to SH mean, are no longer dominant in this near wellbore region. Instead, we have a set of three new stresses which act in cylindrical coordinates and dominate this near wellbore vicinity. Those are the blue axial stress, sigma YY, the red tangential stress, also known as hoop stress, sigma theta theta, and the green radial stress, sigma RR, all acting in the configuration which I show here on the wellbore radius. For this study, we set our wellbore parallel to SH mean, which is a common oil field practice. I will talk a little bit more about that later. And the exact analytical solutions for those near wellbore stresses, as we call them collectively, is given to us by Kirsch theory from 1898 as a function of the in situ stresses, wellbore pressure PW, formation pore pressure PP, and formation Poisson ratio indicated by the Greek letter ni. During drilling, tensile fractures initiate from the radius of the wellbore from an azimuth orthogonal to that of wellbore breakouts. These are known as drilling-induced tensile fractures, or DITFs, and appear on image and caliper logs as narrower than wellbore breakouts, and wellbore breakouts are shear failures. The narrow shape of those drilling-induced fractures makes their orientation with respect to the wellbore easily distinguishable from image logs especially. For a well drilled parallel to one of the in situ stress directions, drilling-induced tensile fractures can exhibit either of two extreme orientations. The most common is longitudinal to the wellbore, like the red schematic on the left, where fractures initiate axially with respect to the wellbore, and the less common is transverse, like the blue schematic on the right, where fractures initiate orthogonally, lateral to the wellbore. Observations of drilling-induced tensile fractures from image logs has significant diagnostic value. The azimuth at which drilling-induced tensile fractures initiate is on the plane of SH max, and their orientation can be used to constrain the magnitude of SH max in the local in situ stress tensor. In the oil field, we can get a direct estimate of SV using overburden calculations which geologists make. And we can get a direct estimation of SH mean from data from leak of testing performed during drilling. SH max is the hardest component of the in situ stress tensor to evaluate. However, using the orientation of DITFs, we can use a graphical method, which I will show later, in order to constrain the SH max. Switching to completion-induced hydraulic fractures, or CIHFs, the mechanism for their initiation is pretty much the same as for drilling-induced tensile fractures. The only difference is that drilling-induced fractures initiate from open-hole wellbore sections without perforation. Completion-induced hydraulic fractures are initiated from perforated wellbores. Similar to drilling-induced fractures, when the well is aligned with either of the in situ stress directions, the orientation will be either longitudinal, like the red fracture on the left, or transverse, like the blue fracture on the right. Generally speaking, for application in low permeability formations, like unconventional shale, transverse fractures on the right are more desired from a productivity perspective. A horizontal well with multiple transverse fractures will outperform the same horizontal well with a gigantic longitudinal fracture. And despite some exceptions, like frag and pag operations, transverse fractures on the right is what we are targeting in today's hydraulic fracture stimulation treatments. In this study, we are investigating the orientation at which those fractures are initiating right from the perforation. This slide shows a chronological series of the main literature milestones in regards to this topic. We begin in 1941 when Biot combined structural displacement analysis with fluid flow to derive his theory of linear elasticity. In 1967, Himson and Fairhurst from University of Minnesota used Biot's theory to modify the Kirsch near wellbore stresses such that they take into account fluid infiltration from the wellbore. In 1951, Anderson publishes his faulting theory, defining the three main faulting regimes: normal, strike slip, and reverse. And in 1978, Barley defines or quantifies the friction factor in rock faults to be about 0.6 to 0.8. Barley used to work for the USGS and passed away 5 years ago. This is important in defining the frictional limits of the subsurface. Then in 1990, we have the first paper discussing the initiation of drilling-induced tensile fractures from the Zoba group in Stanford. And in 2000, Hossein attempts to derive approximations for fracture initiation from perforated wellbores. Lastly, in 2005, Nelson successfully used observation of transverse drilling-induced tensile fractures in West Tuna area in Gippsland Basin, Australia, to constrain the magnitude of the local SH max value there. Having this literature in mind, what we are trying to do is that we are trying to derive orientation criteria analytically for fractures initiating from perforated and non-perforated wellbores, incorporating the effect of fluid infiltration from the wellbore. As I mentioned earlier, Biot combined fluid flow to structural displacement analysis for his theory of linear poroelasticity. This provides the constitutive relationships for a porous permeable solid, whereas fluid moves in and out of its pores, changing the pore pressure. Those pores expand or shrink accordingly. His derivation involved a parameter denoted by alpha b, or the Biot's poroelastic coefficient, which is a function of the bulk modulus of the rock as a whole compared to the bulk modulus of the rock grains. For rocks, this coefficient generally ranges from 0.6 to 1. A few years later, in 1948, Terzaghi used this coefficient to modify the confining stress to define what is known as the effective stress in soil mechanics. Then in 1967, Himson and Fairhurst used linear poroelasticity to modify the near wellbore Kirsch solutions in order to incorporate the effects of fluid infiltration from the wellbore, as this animation shows. As the wellbore pressure increases, fluid infiltrates the pores nearby the wellbore, increasing the pore pressure and therefore increasing their size, and vice versa. Those are the final expressions from Heimson and Fairhurst. And a nice way of confirming their derivation is that if you set pore pressure, wellbore pressure equal to pore pressure, poroelastic effects are diminished, and the equations revert back to the in situ, the Kirsch solutions. Now, Hossein in 2000 had the idea that if we use the values of the stresses on the wellbore radius, we can do a second Kirsch analysis, this time not for the cylindrical wellbore, but for a smaller, also cylindrical perforation intersecting the wellbore, pressurized at the same pressure as the wellbore. This enables us to derive a mathematical expression for the two cylinders intersection point, which is the base of perforation and is what I call here sigma theta theta p. P stands for perforation. When Hossein derived that, he completely ignored the presence of pore pressure. He treated the rock as a linearly elastic, non-porous solid. In 2008, I modified this expression to incorporate pore pressure, and in 2019, I further modified it to incorporate the effects of fluid infiltration from the wellbore. The tangential stress on the perforation base shown here, indicated by the red arrow, is the stress we need to overcome in tension to generate longitudinal fracture initiation. So let's call this the longitudinal fracturing stress sigma theta L. And similarly, the tangential stress in this location here on the perforation base, indicated by the blue arrow, is the stress we need to overcome in tension to generate transverse fracture initiation. So let's call this the transverse fracturing stress sigma theta T. And after a little bit of algebra, those would be the final expressions for the two fracturing stresses for a horizontal wellbore drill parallel to SH mean with perforations